Hi everyone, thank you for coming to the XSS or cross-site scripting lecture. Even though the title says XSS, we're actually going to look at 3 different web vulnerabilities. Ta-da! So we've got the server-side request forgery, SSRF, cross-site request forgery, which is CSRF, and cross-site scripting, XSS. Okay, yeah, so we're going to go into these 3 different web vulnerabilities. The first 2 are to do with request forgery. So it's to do with sort of an attacker tricking a target into doing a request that they didn't intend to do. And the last one is cross-site scripting, which is to do with JavaScript injection. Okay, so the prerequisite content for this is just for folks on video, is introduction to the web. So what we're going to cover in this web vulnerability lecture is HTTP requests, HTML, JavaScript, and also the DOM, which is the document object model. Okay, so let's dive into the first one, which is server-side request forgery. So the way this works is that I'm going to show you diagrams of how the attack would usually work, and then we'll go through some practical examples of how the attack is going to be launched. So what happens in server-side request forgery is that an attacker sends a malicious request to a vulnerable web server. That web server makes a HTTP request as a result of that to an internal resource that trusts this vulnerable web server. And then it returns information from the internal resource. And then the web server displays the information that was returned from that request. So a bit convoluted, but we'll show a working example here. So in blind SSRF, it's the exact same, except the last part from the web server, you don't get any information back. So you might have to use other methods to see what the internal resource actually responded with. Okay, so let's use a very simple example. Let's say I've got a website called myweb.com, and it has an endpoint that lets you change your profile image. And that's how the URL looks like. And you can put in pretty much any URL you want. And the web server goes to, for example, Imgur. It says, right, you want to change your profile image to that. I'm going to request, it does a GET request on this URL. Imgur returns back an image to the web server, and then the web server changes your profile image. So it returns that information to you. So essentially, that's the template of how the attack is going to be executed. So let's say, what if we change the URL parameter to an internal API that is associated with myweb.com? And because the web server is vulnerable, it doesn't do any validation, it sends a GET request to that internal API. So myweb.com/users, and it just returns the user data as JSON. It doesn't check for anything. It just says, right, I'm happy to send that user data to you. So how is that different from making a request directly to the API? If the hacker tried to send a request to that API endpoint, what you would get would be a denied response. So it would be like a 403 forbidden. But because the internal API is on a trusted network with the web server, it accepts that and essentially lets the HTTP request go through and sends a response. So this is an example of a blind SSRF. So instead of putting, for example, a URL to an internal API, what the attacker can do is redirect the request to their own web server. And if the web server is not configured properly, it will return that request with an internal API key, which the hacker can then use to probe around the other internal API resources. So these are different types of URL payloads that someone might use to perform an SSRF attack. You've got, for example, 127.0.0.1, which refers to the local host. So you might be accessing a page or some resource that's usually hidden from the user, but lives on the same machine. And the third one in that table, which is 169.254, 169.254, This is usually known as a service metadata instance. So if you ever use any sort of cloud services like AWS or Google Cloud, this is the IP address or local IP address which you would use to access information like the host name, things like user information, credentials. They all get stored on that instance. So how do you prevent server-side request forgery? The first thing you can do is to sanitize user input. And you're going to hear this quite a lot with the other vulnerabilities as well. But essentially what you want to do is filter out anything that the user shouldn't be able to input. So a good example of this would be, instead of letting the user insert a URL, try and think of how you can limit that input. So if, let's say, you wanted to show the stock of a certain item, limit that input to just, integer IDs. So in that way, the user can't take advantage of the URL redirection to perform an SSRF attack. Return results instead of raw responses. So if you are a server returning a HTTP response, what you want to do is to only return necessary information that the user needs, because any extra information could be used to build a more sophisticated or targeted attack using SSRF. And if you really have to make a request to a different web server, then what you can do is have an allow list, or conversely a deny list. And what you can do is that maintain a whitelist of allowed DNS host names and deny internal IP addresses such as 127.0.0.1. So what this means is that if, for example, your web server has an endpoint that references a URL parameter, so for example, you have to download change your profile image using a URL, make sure you limit the list of allowed host names to a specific set of lists. So you can't redirect, for example, that request to the hacker's web server because it's not in the allow list. Okay, so we're going to go to the next web vulnerability, and this is the cross-site request forgery. But before we get into that, we need to look at a few fundamental concepts in the web. So the first one is that whenever you make a request to a web server, cookies from your browser are added automatically. And I want you to hear that carefully. So what this means is that whenever you're logged in, for example, to an instance of like this bank website, coolbank.com, any cookies associated with the website will always automatically get added to that request whenever you make a request to coolbank.com. Make sense? And the second fundamental concept is something called same origin policy. Same origin policy is a security mechanism that is fundamental to the web. And essentially what same origin policy is that for any given document or script that is loaded in an origin, you are not allowed to arbitrarily read or write from a different origin. So it says here, same origin policy checks whether the protocol, hostname, and port match to allow a document or script to access the requested resource. So this might be a bit confusing because you might think, well, what about requests from one server to another, HTTP requests across different domains? This isn't really talking about HTTP requests strictly. It's talking about if I have a script or document that's loaded on the origin coolbank.com, what exactly can I access from that script directly? So you can see here that if let's say I'm a script on coolbank.com, I can access directory 1 that is on the same machine. I can access index HTML, but if the protocol port or the hostname is different to the origin, then I'm not allowed to access that content directly. But with all policies, there's always exceptions. And the reason why there are exceptions is because for things like form submissions and links, you will want to actually reference a different domain to yours. Otherwise, having every website completely isolated from each other is not really helpful. So the reason why these exceptions exist is because sometimes you have, for example, payment processors that redirect you to different domains to be able to process your payment, or you have links to other websites. It's really important that these features don't get clamped down, because if you completely isolate every website from each other, you wouldn't be able to link websites to one another. Okay, but because there are exceptions, they can be exploited, and so this is what makes up the cross-site request forgery attack. So let's say I'm on a forum, and I'm logged in. So I have a cookie with the session ID. And let's say I wanted to make a request on this forum. I wanted to delete my account, for example. What will happen is my cookie will get automatically added to this request. And so carforum.com will check my post request and check for the cookie and says, right, this is you that's making that request. This is a valid request. And then it says, okay. Now, let's say there's someone on the forum who's made a post and says, hey, I made a new website where you can review luxury sports cars called toyota.com. And I'm curious about it, so I click on that link. And when I click on that link, it takes me to this webpage. So it says, well, okay, that's pretty interesting. But you might think, well, this is not really a luxury sports car webpage. And you might want to actually reply to that original post saying, hey, I think you're just making things up, and like, cool website, but not really luxury cars. But when you go back to carforum.com, what do you know? Your account has been deleted. I think like, what? How did that happen? You have just been a victim of a cross-site request forgery attack. So let's break down what actually happened behind the scenes. Toyota.com had a hidden script in its HTML. And essentially, when you visited that website, it submitted the form that is over here. So you don't see this on the website because it's hidden. But because of the exceptions to single origin policy, it's allowed to submit forms from Toyota.com to Carforum. And so it successfully forges a request. So what happens here is that it forges this post request, which is exactly the same one as I've shown before. Your browser automatically adds that cookie to that post request. And no matter what the origin of that request is, the cookie will be added automatically. And so to carforum.com, the web server, this is a completely legitimate post request, and it will process it for you without complaining. So you might think, well, this is terrible. How do you kind of prevent this kind of attack? So a good way to prevent this kind of attack is using something called an anti-CSRF token. It's generated on the server side, and it usually gets renewed every time you log in or a new session starts. And a copy is sent to the client and hidden in the front end. So it usually will appear as like a hidden field in a form, or it would be a hidden HTTP header. And so whenever you make a request, what your browser will do is add the cookie automatically, as I said before. But this time, because the CSRF token exists in the front end as like a hidden field, it also gets submitted to the web server. And then the web server can essentially check if that CSRF token is valid. So let's go back to the attack I showed earlier. This time, if Toyota.com wants to forge a request, the web server will ask, well, there's no CSRF token. Because the malicious website doesn't have knowledge of the CSRF token, and since it doesn't get added automatically to the request because it's not stored as a cookie, the server will reject the request. Okay, so now we're in the bulk of our, well, this is the vulnerability that I wanted to talk about, which is cross-site scripting. And I don't think cross-site scripting is a very fitting name, I would say, but because Microsoft popularized the name, it's known as XSS. I would call it more like a JavaScript injection. So what if you had control over a website's JavaScript? If you could inject malicious JavaScript into another user's context, these are the things that you could do. You could steal their session cookies. You could traverse and manipulate the DOM and steal hidden fields and CSRF tokens, as I just said earlier. You can execute keyloggers and other JavaScript APIs, such as files and geolocation, or you can redirect and send information to a malicious website. So the JavaScript that enables this to happen, we usually call these cross-site scripting payloads, and we'll have a look at these. So here are three very common cross-site scripting payloads. And the one that I want you to pay attention to is the first one, because this is the one that you will see most commonly and we most commonly use. So we use the alert method in JavaScript, which is usually enclosed in script tags. And essentially on your browser, what you'll see is there's a prompt or a pop-up that shows up on your website. And this is usually used to demonstrate that cross-site scripting is possible on a website. So if you are a pen tester, for example, and you are checking for web vulnerabilities, usually to show that cross-site scripting was possible on this website, you would use this method. But let's say you were a malicious attacker, the kind of payloads that you might use are the second and third one. So the second one sends your cookie to a malicious website, hacker.com, and allows them to read and steal your session or credentials. And the last one is it acts as a keylogger. So every time you make a key press, it will send a request to the hacker's web server. And this is really dangerous because if this payload gets injected on a screen where you're entering sensitive information, then the attacker can basically steal things like credit card information, passwords. So there are four types of cross-site scripting. We've got reflected XSS, stored XSS, DOM-based XSS, and blind XSS. Okay, so the first one is reflected XSS. Let's say you have a website, and the way that the error is displayed is that you've got a URL with an error parameter, and then the text after that is directly inserted into an HTML block, and it shows up as an error. Since the user input is directly reflected in the HTML block, an attacker can inject JavaScript by just changing the value of the error parameter. So what do I mean by that? Let's say in that URL, I put in the payload that I mentioned earlier, so an alert method. What happens is that payload gets injected directly into the HTML block. And because the browser doesn't differentiate it, or it's not encoded as text, the browser will execute that directly, and you'll get a prompt and a pop-up show up on your browser. So how can an attacker use this to perform a reflected XSS attack? Let's say we've got a hacker here and we've got Alice. The hacker sends Alice an email, and the email says, "You've got an outstanding direct debit of £155. Please make a payment here." And so that hyperlink actually leads to this URL. So you can see here that the attacker has used a reflected XSS attack in the link. And when Alice opens up this link, what she's going to see is it goes to the actual bank page and you just get a generic unknown error. But what's actually happening behind the scenes? Alice's browser essentially loads a JavaScript file from the hacker's web server, and then that script sends cookies, credit card information, and passwords to the hacker's web server. And so now the hacker has access to all of Alice's credit card information and probably her bank account too. Okay, so the second one is stored XSS. It's kind of similar, but there's one main distinction. So let's say we're back on carforum.com, and when you want to comment on the website, you send a post request with a text payload. So here, let's say I wrote a comment, "Hello world," under a post. And what happens is whenever you send this post request, the web server creates a new comment object that persists in database. So here it creates a new comment object, "Hello world." And whenever someone views that comment, the web server will send that comment object directly in a HTML block to you. And so that's how you get to see the HTML block as a comment. This affects every user. So every user that looks at your comment will get that response back from the server. And so you can kind of intuitively see how a stored XSS attack might happen. Let's say I'm sending that same post request, but this time I've put in my XSS payload. I create a new comment object, but this time it has the HTML script tags in there. And anybody who loads up this comment or reads my comment on the forum is gonna get an alert. And this is especially quite devastating because it essentially means that I only need to send in one payload to the web server for everybody who reads the comment to be affected. So what I'm going to do is I'm going to show you a very short video of a very hilarious example of cross-site scripting. If it will load, of course.
Okay, all right then, that was entertaining. So, let me put it this way. You guys found a vulnerability in the chat client that... Don't mind me. Oh my goodness. I'm just going to sit back and sip my tea. Somebody get time shifter in here. He's got to see this.
So yeah, that was a quite hilarious example of cross-site scripting, but you can sort of see that if someone actually put in malicious payload in there, that would affect what you would see on the screen. Obviously, I think Twitch has probably patched that now, because you wouldn't want like JavaScript payload across your streamer, and then they get hacked or something. Okay, so the third type of XSS is DOM-based XSS, and I've just put a recap here to what DOM actually is. The Document Object Model, or the DOM, is a programming interface for web documents. So it's like a tree-like structure which represents the HTML document, and that's how programming interfaces can interact with the HTML document. So, add in style, color, things like links and attributes. So let's say we have a website, I called it unsocial.com, and you can change the color of your profile banner by specifying a color after the color parameter in the URL. So here I've got the color blue, and let's say I wanted to change it to pink, I would just change the URL to pink. So seems great and dandy. But the DOM-based XSS, it doesn't interact with the server side via requests like reflected or stored XSS. This time, it just affects how the website is rendered on the client side. So let's look at how an attack is possible using DOM-based XSS. So again, I put my payload after the color parameter, and you can see here that there's no color now on the banner. But what happens is it runs the JavaScript directly. So how is that possible? So you can see here that the difference in this payload is that I've actually escaped it with a style tag. And if I look at the code that's behind my website, I'm using a method in JavaScript called document.write. Now, this is considered one of the unsafe JavaScript methods that can interact directly with the DOM. And we call these JavaScript sinks. So you can see here that because I'm writing that specific block of HTML into the website, it escapes the style tag, it runs the script as JavaScript, and the browser executes it, and I get the alert. So what's actually happening in the DOM then? So before, you can see that in the style tag, it's got a property, and the color of the body is set to blue. But because I've changed that payload to insert a script, what happens is that the API interacts directly with the DOM, and it inserts this script tag with the alert method. So we can eliminate the risk of DOM-based XSS by avoiding the use of these unsafe methods, which are called sinks. So for example, the fix here is to safely extract the keyword from the URL. And instead of using document.write, I can just directly change the color attribute of the body and setting it to the color that I extracted. So these are JavaScript sinks that you would want to avoid, which is the inner HTML, outer HTML, document.write, element.setAttribute, eval, setTimeout, and setInterval. So all of these methods interact directly with the DOM, so you will want to avoid using these sinks directly with user input. If you have any questions, just feel free to ask, or stop me if I'm going too fast. Okay, so with DOM-based XSS, you can see here that when we put in the URL with the color, it interacts directly with the JavaScript, but it's not actually sending a request to the server to change the color of the banner. So an attack can happen if this attacker, for example, he sends Alice this link again, and he changes the color parameter to the payload that I put earlier. What happens is when Alice loads this web page, it's directly vulnerable, even though it doesn't require sending the payload as a request to the server first in order to run the JavaScript on the victim's browser. So this kind of attack it will directly affect any person who opens the link without actually having to interact with the server first. And the last one is blind cross-site scripting, or blind SSS. And this is very similar to stored XSS. So, for example, let's say I'm back on carforum.com, but I need a bit of help, and I want to contact a member of staff on the forum for support. So I write in a contact form, please help me. What happens is I send a post request to the server with the same payload, please help. And the difference now is that, yes, it does create a new support ticket object, which with my text, but I can't view the ticket directly. Only a staff can view this. So essentially, the text is inserted into a HTML block again, but only the staff has access to actually seeing the support ticket. Right, so let's see how a blind XSS attack might work. If I change that text payload to a script, and that script had a malicious payload, then what would happen is that I'd send this contact form to the web server. The web server would store it as a support ticket. And when the staff actually views the support ticket, then it will run the malicious payload and sends over cookies and credentials to the web server. But the difference is I can't actually prove when or if the attack will work until the staff actually opens up the support ticket. And so the main distinction here and between here and stored XSS is you don't directly get to see the effects of your attack. So how do you prevent cross-site scripting? So here are the main principles for preventing cross-site scripting vulnerabilities in your website. First, sanitize and filter user input on arrival. Only allow necessary input. So this is very similar to what I showed earlier for preventing SSRF, but the difference is, as a rule of thumb, you don't want to write your own sanitization logic. What you want to do is use a library like DOM Purify. So what does the library do? It takes any user input and essentially it looks at the input, it sanitizes it, and it only outputs any HTML that is clean. Essentially, it doesn't have any of the unsafe methods, things like onload, SRC, hrefs. It just outputs clean HTML and it removes everything else. And the reason why you don't want to write your own sanitization logic is because XSS is so advanced that people have found workarounds to many different types of filters. And because if you try and write your own filters and you think that your website will be secure, it's very easy for people to sort of escape your filters or find other keywords that can be substituted in to perform the same attack. And the second one is to encode the output. That just means that for any output you want to show or anything you want to insert into HTML block to show to a user, make sure that you encode it. For example, encode your reflected input strictly as text. Don't let it show up as HTML blocks, which the browser can directly render onto the user's web page. Use content type headers in HTTP responses when you expect non-HTML and non-JavaScript content. For example, if your response is supposed to return an image, don't, for your response, limit what the user can see by setting a content type header, because essentially when you set the header, you can't return anything other than the type specified in that header. So if, for example, you're supposed to return an image, you can't return any HTML or JavaScript, which basically limits the attack window for this cross-site scripting attack to happen. And the last one is kind of obvious. If you receive a suspicious URL or a link, try and scrutinize them before clicking on the hyperlink. So this is if you receive an email and you essentially want to see whether that link is safe or not. Try and have a look whether that link has any things like script tags or like weird encodings that might resemble an XSS attack. And then you can sort of identify beforehand just by looking at the full URL if you will be a victim of a cross-site scripting attack. Okay, so in summary, these are the 3 vulnerabilities we've covered and the prevention measures for each of these vulnerabilities. So what I wanted to highlight here is there's something called Google XSS game, if you're interested. Essentially, you go through, I think, 5 or 7 levels of cross-site scripting exploits or bugs that you are supposed to try and figure out how to bypass and use to your advantage. It's really helpful if you want to learn XSS in your own time and you want to give it a try. I highly recommend this website. It's free as well. You can basically click on the link and try it for yourself. And another thing that I wanted to highlight for this month is the 2025 Advent of Cyber for TryHackMe. This is completely free as well, which is really good. It's 7 days of cybersecurity related challenges. So it's not just to do with the web, it's to do with things like Linux, the command line, network scans. They've got a whole bunch of challenges and each one unlocks each day. So the first one came out yesterday. I would highly recommend you to try it over the winter holiday if you're interested. They're really fun and they're pretty easy, but they also have like side objectives that are quite challenging. So I would recommend you to try the Advent on Cyber on TryHackMe if you have time and if you're interested. So here at the end, I've just got the links to the videos that you can watch to learn a bit more about the 3 vulnerabilities that I did. And I've also linked the video to the Twitch clip that I put into this slide.